in front of you. Welcome back once again after a few days. Few days feels like a week. So before I start, let me know if everything is all right and how are you all guys? We can say hope. Is everything all right? Good morning, Harry. I underestimated this cold, but it gave me proper calculation. Okay, so today in this session we'll be discussing Karnaugh map and logic gate. We'll first discuss, then we'll go for Karnaugh map. All the things are all right. Audio, video, everything is all right now. Especially the audio. Are you ready to go? I am fine for the time being. Not fully recovered, but sufficiently recovered to continue the session. Let's try. Will not go heavily, but we have to continue. Okay. Little buzzing sound. Okay, let me just have to continue. Little buzzing. Okay, just a moment. Let me do something about it. Okay, would be a little bit better. As I expect. Okay. Good morning, Dhan. Ajay. Where is Murli? The buzzing sound is not enough. Just bear with me, I'm just testing, and once the sound will sound good, we can start. Okay, let's compromise. I think this much we can do for the timing. Not going timing. Okay, can you continue with this like this? Can you continue with this like this? Okay, so let's start with this Boolean algebra and Karnaugh map. Okay, okay. So we'll cover today logic gates. Now, in logic gates, we primarily will start with our discussion with OR gate, AND gate, and NOR gate. So you already know about this thing. Let's quickly just revisit those gates. Firstly, we'll go for OR gate. OR gate. So OR operation refers. So in these logic gates, what happens? We have two or more than two inputs and one output. Okay, this is the basic fundamental thing. So how the output is decided? A is equals to A. We do not read it like A plus B. We read it like A or B. Okay. So in the OR gate, the output will be 1 if any of the input is 1. So the best way to understand its characteristic is to look at its truth table. how the input decides the output, we format it in a table that is known as the truth table. Let's say we are giving A and we are getting, if any of the input is high, then the output will be high. 0, 0, all the inputs are low, so the output will be low. And if any of the inputs are high, the output will be high. Sorry. Yeah, this is a simple OR gate. Now, how does this OR gate look like? You know it. It looks like this. We give two inputs, A and B, and you get Y is equals to A plus. So this is pretty much about the OR gate. Let's go for the AND gate. AND gate or the multiplication gate. Here the output Y is represented by A dot B. So how do you read it? Y is equals to A and B. Okay. A dot B we do not read here. We will read it A and B. Okay, this will serve the purpose of multiplication. So the output will be 1 only when both the inputs are 1. Output is high only when both the inputs are high. How about its truth table? Let's talk about the truth table. Truth table of AND gate. What changes we will have? 0 into 0, that is 0, that is okay. 1 0 0 1 0 0, this is 1. Now, how does it look like? You know how does it look like? This is your Y is equals to A and B. Okay. The next gate is NOT gate. Here the output Y write as A bar. So what it basically does, it inverts the input. So this does the process of inversion or complementing. So let's say if you talk about the truth table, we have the input A, we'll make it A complement. So if you have 0, we'll make it 1. If you have 1, we'll make it Sometimes it is represented in this way. So this is your NOT gate. Y is equals to not A or A complement. This is read as Y is equals to not A. Let's talk about few of the laws of the Boolean algebra. Laws of Boolean algebra. A few things, a few formulae you need to remember, like how the basic OR, and NOT gate produce outputs. So A or 0, what will be its value? A plus 1, A plus A. Tell me what A plus 0 is? A. A or 1 is how much? These things will be useful when we solve problems. This will be 1. A and A. A plus A or A is A. This one is important. A plus A complement. What will be its value? This is 1. A and O. A and 0, you can say. This will be 0. A and 1. What it will be? It will be A. Look, we are not simply doing mathematical calculation. We have to keep in mind the logical operation. The logic gate perspective should be kept in mind while writing these results. These are standard results. For an example, A and A. What will be its value? Tell me. A and A. What should I write here? A and A is equals to how much? A and A complement is equals to A complement is equals to A dot A is A dot A complement is 0, A complement and A double complement is A. This result is very important. A double complement is A. When we will actually calculate the minimum number of NAND gates, then this operation is done. If you want to make a circuit using NAND gates, so you have to take the double complement of the logical expression given to you. We'll do them later on. Now there are various laws in Boolean algebra. The laws which you see in your mathematical physics also, like commutative laws. Let's talk about commutative laws. Commutative laws. A plus B is same as A B plus A. A dot B is same as B dot A. Okay. Then we have associative laws. Associative laws. A plus B plus C is equals to A plus B plus C. A dot B dot C is equals to A dot B dot C. Now there is a very important law, distributive law. Distributive laws. What does it say? It says A dot B plus C. This is equals to A dot B plus A dot C. So up to this much, everything is looking to be very as usual. But there is a law now which I am going to give you. Let's say if you have A, instead of dot, we have plus. Instead of B plus C, we have B dot C. Do you know about this law? A plus B dot C. This is important, and many of the time questions are set from this. This is the distributive law. A plus B dot C. What will you write? Look, this will be written in a similar manner to this. So you can write it as A plus B into A plus. Remember this one. There are some miscellaneous laws. For an example, if you add A and AB, what you get? Let's say if you multiply A with A plus B, A plus A complement B, A into A complement plus B. Tell me the first one, A plus AB, what you can write? It is A, if you take common, 1 plus B, 1 plus B is 1, so that is A. Okay. Tell me about the next one, A into A plus B. Look, A plus B, it must be 1, right? Whether A may be 0, B may be 1, or B may be 0, A may be 1. So we can just write it A, right? Try to understand it. Look, A plus B will always be 1 if I consider. The 1 into A is A. If you say that both are 0, okay, both are 0, then again if you put equal to A, that is 0. A plus A complement B. Second relation you understood now. A plus A complement B. This is written as A plus B. This one, A times A complement plus B is equals to AB, because A complement is equals to 0. Okay, let's move on. Let's go to a principle called duality principle. So let me just show you these relations. A plus 0 is equals to A. A plus 1 is equals to 1. A plus A is equals to A. A plus A complement is equals to 1. Now I am writing another set of equations. A dot 1 is equals to how much? A. A dot 0 is equals to 0. A dot A is equals to A, and A dot A complement is equals to. So what observation you can make in this? What observation you can make in this? You can see that the plus or operation has been replaced by AND operation, right? OR operation has been replaced by AND operation, and 0 has been replaced by 1. OR operation replaced by AND operation, and 1 has been replaced by, and we got this result. Look, 1 has been replaced by 0, 1 has been replaced. So this is the duality principle. So note that in all the above pairs, of rows, one can get one rule from the other by interchanging the OR and operators. Okay, look, and is there is a term and in the English language also. So whenever you want to represent AND gate, you will write capital, okay, AND, in this way. Interchanging the OR and AND gate or AND operators, and by replacing zeros with ones and ones with zeros. And you see, in all the pairs, in all the rules, this has been followed. This property is called the duality principle. This property is called duality principle. Okay. Let me know once it is done, then we'll go for the next one, De Morgan's theorem. Okay, look at its De Morgan's theorem. This is one of the most important theorem in this Boolean algebra. De Morgan's theorem. Look, one of the most powerful identities used in Boolean algebra is the De Morgan's theorem. In words, we can express it in this way. The first theorem, the complement of a sum of variables is equal to the product of the complements of the individual variables. Now read it and look at this. The complement of a sum of variables a, b, a plus b plus c. Complement means bar. The complement of a sum of variables is equal to the product of the complements of the individual variables. Product of the complements of the individual variables. A complement dot b complement dot c complement and so on. Okay. Number 2, the complement of a product of variables. Complement of a product of variables a dot b dot c is equal to the sum of the complements of the individual variables. Sum of the complements of the individual variables. A complement plus b complement plus c complement. These two mathematical formula you need to remember, and it will be used many times. So it is like these theorems are very powerful tool because it can change the OR logic and AND logic into each of them. So you have OR operation here, you see a plus b plus c. From OR operation we have just converted into AND operation, and here AND operation was there, a dot b dot c and so on. So we have converted into an OR operation, a complement plus b complement plus c complement and so on. So that is why this becomes very important. Let me give you one problem. Just note down these two theorems. Okay, it will be a practice for you. A plus b plus c dot 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 complement is equals to a complement dot b complement dot c complement and so on. A dot b dot c complement is equals to a complement plus b complement plus c complement and so on. So let's take a problem. Problem reads like this. Simplify the expression. We have this expression of ABC, A complement BC, A B complement C, A complement B, A complement, A complement, A complement C, A complement, B complement, A complement. Can you do this? So let's go step by step. Look, if I take A, B, C, and here you can see if I take A, B complement C, then you can take AC common, then B and B complement will make a formula. Next, A complement BC. Try to find some term from where we can take common. A complement we have, so we have to find out A, B, C. Is there any A, B, C? A, B, C is not there, but we have A complement, B complement, C. So we can take A complement C common. Okay. Next, what we have? A complement B complement plus A complement B complement. Can you write it in this way? Now here we take A common, AC actually common, B plus B complement times C. Here we are taking, let's say, A complement E plus B complement C, and here we are again, actually B and B complement we want to extract. Now you know B and B complement, B plus B complement is 1, so it becomes AC plus A complement C plus A complement. Now again you can take C common, A equal plus A complement into C plus A complement C common. A plus A complement is 1, so this becomes C plus A complement. So C, it is like C into 1 we can write. Why we have written it? Because once you are able to write C into 1, what you need A complement. Okay, so let's do another thing. If I write 1 plus A complement, so 1 plus something, it always be 1, right? If it is 0 or 1, you know, if any of the input is high, the output is high for OR gate, so we can write it in this way. Now you see we have C A complement, and here we have C complement A complement. So C remains plus A complement. If we take common, we have C plus. So C plus C complement is 1. 1 into A complement, it becomes A complement plus. This is the final answer. Look, these things, there is no straightforward rule or steps that you have to do it this after this after this. We have set up rules that you have to keep in mind, but you have to proceed it in such a way that you get one of the answers correct. Now this thing, you see, we have to think a lot while solving this. But if you use Karnaugh map, we will not have to worry this much. Using Karnaugh map, we can do it very simply, and you will get it at the most simplified expression. So that is why Karnaugh map is important. We'll talk about it, but let's learn this also. Is there any question from this? Anyone has any question? You can ask. Hari, Ajay, Vantage, Dharan, Murli. Anyone has any question, you can ask. Okay, let's go for another problem then. Simplify the expression AB complement plus A complement plus AB full complement. Do it. Okay, could you do this? So you can use De Morgan's theorem. 0? Yes, very good, Haran. Let's look at the solution. AB complement plus A complement plus AB whole complement. AB complement, using De Morgan's law, we can write A complement plus B complement plus A complement plus AB whole complement. Now A complement plus A complement is A complement plus B complement plus AB. We have used this property, like if you have two variables repeated, we get the same variable. Now, what is A complement? Look, we need B somehow. We have B complement. So A complement, we can imagine that 1 is multiplied. So 1 plus B, if you do, times A complement, then we will get some formula this way. So this is equals to A complement plus B complement plus A complement B plus AB. Can you write it? This is equals to A complement plus B complement plus, if you take B common, we have A complement plus A times B. This is equals to A complement plus B complement. A plus A complement is 1. 1 into B is. Now, what is B plus B complement? B plus B complement is 1. 1 plus A complement is 1. 1 complement, that is. Understood? Let's move on to few more problems so that you understand it very well. So you have to play around, okay? Simplify the expression AB plus A complement C plus BC. Do it. Look, AB plus A complement C plus BC. How can go? AB plus A complement C. BC is not standing alone. So we can write BC into 1. So BC into 1. What you require? We require A and A complement. So 1 we can express at A plus A complement, because A plus A complement is 1. Okay. So this is AB plus A complement C plus ABC plus A complement BC. The order doesn't matter. You can write BC and ABC are same. It's not matrix. Okay. So AB we can take common, 1 plus C, and A complement C we can take common, 1 plus B. So AB plus A complement so this BC part doesn't carry any weight. So this is the simplified form. You cannot simplify more than this. Let's go for another one. Simplify the expression. A complement BC plus AB complement C plus ABC complement plus ABC. Do it. Okay. So if you look at this problem, here we have A complement BC. So BC related term is there here. So let's take that. A B complement C, and here A BC complement. So what you can do, we can write it in this way. Let's keep it together. A B complement C plus ABC we can write, plus A B C complement plus ABC. Can you write it? Tell me. Writing ABC thrice is same as writing ABC once. A plus A plus A is A. We have seen this. All the things we have already talked about in the formula. A plus A is equals to A. So this is the property, A plus A plus A plus is equals to A. So from the first expression we can take BC common, and we have A complement plus A. In the next, what you can take, we can take AC common, B complement plus B. From the last one, we can take AB common, B complement plus C. So we have BC plus AC plus AB. Okay, this is the simplified form. Clear? Look, or and not, these are fundamental gates. Now there are some logic gates which are known as universal building blocks or universal logic gates. NAND and NOR, these two gates are called universal gate. Why it is called universal gate? Because by the repeated application of these gates you can build any of the Boolean expression. So we will talk about it. This NAND and NOR gate, they are made up of the fundamental gates AND and NOT gate, but this NAND and NOR gate can design any gate. So that is why they are called universal gates. Or and not, these are basic building block. Is it done? Now these two gates are the most important one. Universal building blocks. Look, if I talk about OR and NOT gate, so these are basic building blocks. On the other hand, NAND, NOR, these are the universal building. And design by the repeated application of these blocks, repeated application of these gates. That is why these are called universal building blocks. So let's talk about the first one, the NAND gate. The name speaks for itself. NAND means not plus AND. Okay, so how we got the AND gate? AND gate we got it in this form. This was the AND gate, and a dot, a bubble is given to it at the end. Okay, so we have two inputs A and B. So A, B, NAND is equals to not plus AND. So AND operation A dot B because of this NOT operation, we will have A dot B complement. It is a combination of AND and NOT gate. Now, what about its truth table? Truth table for a 2-input NAND gate. A, B, Y. Obviously, 0, 0 is 1, 0, 1, 0, 1 is 0, so this is 1, 1, 0 is 1, 1, 1, 0. Now, let me tell you an interesting fact about this NAND gate. You see, the Boolean expression y is equals to A dot B complement. Now, if we apply, let us say, De Morgan's theorem, it can be written as A complement plus B complement. Using De Morgan's theorem, can you write it? So, A complement, how do you get A complement? A complement, let us say you have an input A. If you take NOT operation of this, what it becomes? A complement. We have B, you take NOT operation, this is called bubbling, okay, it becomes B complement. Now, if you join them by an OR gate, so what does it become? A complement plus B complement, and it can be equivalently expressed in this way. This thing, this is A, this is B, let us say. So, instead of showing this much, we can just simply show this, like this. So, these two are equivalent. This is also A complement plus B complement. So, what we can say about the NAND gate? We can say, look, if these dots or bubbles were not there, it is simply an OR gate, right? So, NAND gate is nothing but bubbled OR gate. Thus, an NAND gate is equivalent to a bubbled OR gate. Is it clear or not? Now, as I told you, you can, using NAND gate, you can design any gate. So, let us take some example of that. How using NAND gate we can design different gates. So realization of different gates using NAND only. Let us say NOT gate, you want to express NOT gate, but NOT gate using a NAND gate. So what you gonna do? We have an input A. So for a NAND gate you require at least 2 inputs. Okay na? For NAND gate you require 2 inputs, but for NOT gate there are only 1 input. So what you can do? You can make 2 inputs like this using this A and A. Then you can connect it to a NAND gate. So A into A is A and A complement. So your Y will become A complement. So this is how you can get a NOT gate using NAND gate only. Let's say you want to get AND gate. AND gate using NAND gate. So 2 inputs A and B. Just keep in mind that you can only use NAND gate, nothing else. What it produce? AB complement, right? But AND gate is AB. So if we take another NAND gate, then AB complement, look, AB complement, AB complement. So and its complement. So your Y becomes AB. So you get the AND gate. Let's say OR gate you want to design. How will you design? Using NAND gate. Can you do it? Give it a try. Look, in OR gate we have 2 inputs, A and B. Look, the best way to do this is to take double complement. Instead of putting 2 NAND gate, if it is replaced by 1 NAND and 1 NOT. No. What does it say? Using NAND only. So we are not allowed to use any other gate, only NAND gate. That is a challenge, right? You cannot use other gate. Look, the best way to do such things would be this property using this a y double complement is equals to y. This is the property. Let's say we want to make A plus B. So y complement A plus B complement and its whole complement. So what it gives you? A complement dot B complement full complement, right? You need A complement, so you have to make it 2 input. You can do it in this way. Using a NAND gate you can get A complement. We require B complement. So B 2 input NAND gate B complement. You have to multiply and take complement. Multiply NAND gate. So that can be done in using another NAND gate. So this is A complement dot B complement whole complement, and that is what y is equals to A plus. Clear? Look, y is equals to A plus B was there, and y double complement is equals to y. So writing y is equals to A plus B and writing y is equals to A complement dot B complement whole complement is same. So whenever you have been asked to express using NAND gate, what you will do? You will use this property. You will take double complement, and after that you can use De Morgan's theorem to get it in a simplified form. Clear now? Let's talk about its counterpart, NAND gate. So NOR gate. NOR gate means not and OR. Next, let's go for NOR gate. As per the name suggests, it's a combination of NOT and OR gate. So A, B, OR gate. This operation does the OR operation. Then you put a bubble which is complement, OR plus NOT, NOR. A plus B, and this bubble does complement. So how we can get its truth table? A, B and Y. Okay, so 0 0, 0 plus 0 complement, 0 plus 0 is 0, 0 complement is 1, 0 plus 1 is 1, 1 complement is 0, 1 plus 0 is 0, 0 complement is 1 plus 0 is 1, 1 complement is 0, 1 plus 1 is 1, 1 complement is again. Now apply De Morgan's theorem again. Y is equals to A plus B complement. We can write A complement dot B complement. A complement is what? And B complement and this AND operation. So we can equivalently represent, let's say this is your A, this is your B. So bubbled operation makes A complement and B complement. So it is like then their AND operation. So what does it mean? Thus the NOR gate is equivalent to a 2 input bubbled AND gate, na? Bubbled AND gate. Can you say it like that? Now, as this is also a universal building block, means we can express any Boolean expression using this NOR operation. So, let us talk about them. Realization, realization of different gates using NOR only. Look, most of the time NAND is mostly used, NOR is not much used. Let us talk about NOT gate. NOT gate. So, NOT gate is A complement. So, A we take, we need two input for this NOR gate. So, y is equals to, you see, A plus A is A complement, NOT gate. Let us talk about OR gate. OR gate is simple. Can you give it a try? OR gate. OR gate is A plus B. So, it has already an OR gate inbuilt. So, if I start with A and B, and if I use one NOR gate, so A plus B complement. Now, what you require, you just need to remove this complement. If you just made it pass through another NOR gate, A plus B complement and A plus B complement is A plus B complement, and this bubble makes it A plus B complement complement. So, that is y is equals to A plus B, OR gate is done, AND gate. Let us say A and B. Look, AND gate y is equals to A dot, right. If I take double complement, we get our y is equals to A dot B back. So, it is A complement plus B complement whole complement. So, you have to first make A complement. So, we need two inputs, NOR gate, A complement, NOR gate, B complement. Now, we have to add them and take complement. Understood? Okay, let us do one thing. Let us continue it from the next class. Actually, I am not able to take longer sessions. Okay, I am not fully recovered yet, but it's okay. I have sufficient energy to take this much. So, we will continue from this XOR gate, then XNOR gate, then we will go for the Karnaugh map. Okay. No, those are Look, only NAND and NOR, these are universal gate. You can design any gate using NOR gate and NAND gate. NAND and NOR. Okay, especially NAND is mostly used. In the next class, we will start with XNOR gate and XOR gate. Then we will go for other things. After that, we will go for the Karnaugh map. Okay. Hello, bye bye. Have a great day, guys, and we'll continue on the next day. XOR and XNOR and NAND as NOR, vice versa, not mentioned for universal gates. Acha, you are talking about here. No, only this NAND gate and NOR gate, na, universal gates. Okay, we'll take up the question in the next class. Okay, in the beginning, you can take all your questions, or you can also DM me. Okay, bye bye.